Hi, my name is Dr. Miguel Mitchell, founder of ChemAnimation.com. Welcome to the first lecture in the OChem 1 Intensive series entitled Structure and Bonding. When you want to figure out the electronic structure of a molecule, all you really care about are the valence electrons of the atoms. So, how do we figure out valence electrons? These are the ones that are beyond the last set of electrons matching a noble gas. So for example, carbon, which has 6 electrons, since it has 6 protons, the first 2 electrons match helium, a noble gas. So there are 4 valence electrons that we care about. With sulfur, that has 16 electrons because it has 16 protons. The first 10 match neon, a noble gas, so there are 6 valence electrons. Valence electrons create the bonds that make up molecular structure, so that's why we're interested only in valence electrons. Now, these valence electrons, as I've mentioned, make the bonds, but there are 2 types. Nonmetals make covalent bonds, that is, they share 2 electrons, with nonmetals and metalloids, which are the elements in group 3A, like boron and aluminum. Nonmetals also make ionic bonds where they steal electrons when they're bonded to metals. So they make ionic bonds with metals. We're going to focus mostly on the covalent bonds. The number of bonds needed for an atom to be happy or stable matches the number of electrons that it needs to look like the next noble gas. And this ends up fitting what's known as the octet rule. So if you consider carbon has 6 electrons, it's going to need 4 electrons to be like neon, which has a total of 10. Thus, carbon makes 4 covalent bonds to other nonmetals or metalloids. Since carbon starts off with 4 valence electrons, and it gains or shares 4 electrons from bonds, that's a total of 8. That's where you get the idea of the octet, octet meaning 8. Sulfur has 16 electrons, so it needs 2 more to be like the nearest noble gas, argon. So it makes 2 covalent bonds to do this with other nonmetals or metalloids. Now, sulfur has 6 valence electrons, so when it gets 2 more bonds, that's like it's getting 2 more electrons. That's a total of 8. Again, the octet rule applies. Group 3A is a weird group. Boron and aluminum each have 3 valence electrons, but they need 5 more electrons to be happy. So if they are able to make 3 bonds with those 3 electrons, they'd get 6, which wouldn't be an octet, so that would make them unstable. If you consider borane, the simplest way to write that is BH3, and alane, AlH3. In both of these cases, the central atoms are unhappy because they don't have an octet. There are 2 ways for boron and aluminum to be stable. The best way is if each of them can get an extra pair of electrons. So they can pick up 2 electrons from some other atom, donating a lone pair, and everything's great. Consider borane, BH3. If it picks up a lone pair from hydride, H-, it will form BH4- or borohydride. In that situation, boron now has 8 electrons around it, which makes it happy. It's an octet. Alane, similarly, can react with hydride to form AlH4- or aluminum hydride, and now aluminum has an octet. A second suboptimal way for boron and aluminum to be more stable but still not happy, if there's no lone pair donor around, they can kind of double up. So if you look at diborane, B2H6, this is actually the simplest compound of boron and hydrogen. There really isn't any BH3 that is stable, but B2H6, diborane, is semi-stable. At least it's a little happier. Boron has 2 regular bonds to hydrogen, the one shown as wedges and dashes. So there's 2 electrons in between each of those atoms. That'll give it 4. Now, notice that the hydrogens in the middle are being shared by two borons, so that makes it three centers, two borons and one hydrogen. But there are only two electrons, one dot, you might say, between each BH bond, and that gives you the correct number of electrons, but you have strange bonds. These are called three-center, two-electron bonds. So BHB has two electrons and three atoms, or three centers. What this does is allows the boron atoms to effectively share the pain of not being octets. So each boron atom gets the normal set of 6, but if you consider the smearing of the electron density from one BH bond to the other, it's almost like it's getting closer to 7 electrons. You know, if you think about it, 2 for each BH bond, and maybe a little bit more from one of these three-center two-electron bonds. You know, it's a matter of conjecture, but it's certainly better off than if it were simply BH3 because of the spreading out of the electron density from one boron atom to the other through this intermediate hydrogen atom. Now we're going to look at what I call the uncharged happy atoms. Okay, these are atoms that don't have a charge, no plus or minus charge, but they have enough electrons when they form a bond or bonds to look like the nearest noble gas. So let's consider hydrogen first. It makes one bond, so now it looks like helium. In HCl, there are 2 electrons shared between H and Cl, so hydrogen is happy. If you have more than one bond, now we have to consider molecular geometry, so the shape of the molecule, which follows valence shell electron pair repulsion model, or VESPR, that you learned about in general chemistry. The group 4A atoms form 4 covalent bonds. For example, carbon, when it does that, will be like neon. Silicon will be like argon, etc. when this occurs. If you look at carbon with 4 single bonds, 2 will be in the plane, drawn just as regular lines. 1 will be a wedge coming towards you. One will be a dash going away from you. So these bonds point toward the vertices of a 4-sided object, a tetrahedron. The bond angle is 109.5 degrees. You can also get carbon with 4 bonds by having a double bond and 2 single bonds. In that case, the central carbon atom will have its 3 attached atoms displayed in a flat picture, which is known as trigonal planar, and the bond angle will be 120 degrees between each set of 3 atoms, so between each pair of bonds. In a situation where carbon has a triple bond and a single bond, the bond angle is 180 degrees and it will be linear. In group 5A, nitrogen, phosphorus, etc. form 3 covalent bonds to be like their nearest noble gas. So when nitrogen forms 3 bonds, it also has a lone pair. That creates a shape which is known as trigonal pyramidal. So it looks like those bonds are pointing to a triangular base. The bond angle is 109.5 degrees. And this is the shape of ammonia. In the case of nitrogen with a double bond and a single bond, and still one lone pair, now you have a bent shape where the bond angle is 120 degrees. This is true for imine. For hydrogen cyanide, you have nitrogen with a triple bond and a lone pair. There aren't 2 bonds attached to nitrogen, so there is no bond angle. Continuing with the uncharged happy atoms, we are now in group 6A, and those include elements like oxygen and sulfur, which form 2 covalent bonds. If you look at water, oxygen has 2 bonds and 2 lone pairs. The bond angle is about 109.5 degrees, and it's a bent structure. In formaldehyde, we have a double bond for oxygen and 2 lone pairs. Oxygen is only attached to one other atom, so again, there's no bond angle. For group 7A, These are the halogens. They each form one covalent bond, so no bond angles are involved here. So we have in the bonding to hydrogen, the acids HF, HCl, HBr, and HI. Now atoms don't have to be uncharged to be happy. We can also have charged happy atoms. The way to figure out the charge is that you need to calculate formal charge, or Fc. And that's the number of valence electrons minus the number of covalent bonds minus the number of unused electrons, which are usually the lone pair electrons. If you have one fewer bond than normal, okay, so that means, for example, with carbon, you have 4 bonds, you take away 1, you have 3. In order for that carbon atom to be happy, it must have a negative charge. So if you take a look at carbanion, the central carbon has 3 bonds to hydrogen. That's 1 fewer than normal. It also will have to have a lone pair for the octet, and the bond angle is about 109.5 degrees. The shape of the molecule is trigonopyramidal like ammonia. If you calculate the formal charge on the carbon, that's 4 valence electrons minus 3 bonds minus 2 unused electrons. You count each electron in the lone pair. So that gives you a charge of -1. For the amide anion, which has a bent shape, you have 1 bond less than nitrogen normally has. Nitrogen normally has 3 bonds, so now it has only 2. So you expect a negative charge. 2 lone pairs and 2 bonds are present. So when you calculate the formal charge, it's 5 valence electrons for nitrogen, minus 2 bonds, minus 4 unused electrons. So that gives you a -1 charge. For hydroxide, oxygen has 1 bond instead of typical 2. It has 3 lone pairs. So now oxygen has 6 valence electrons, minus the 1 bond, minus 6 unused electrons. So that gives it a charge of -1. So you can see in all these cases, 1 fewer bond, and the atom has a negative charge if it's still happy. Now, you can also be stable if you have 1 more bond than normal, and this can only happen if the original situation, the atom had a lone pair. So it's now donating that lone pair to another atom that doesn't have any electrons and is crying, I need electrons, help me, right? So the atom with a lone pair donates its pair to make a bond to another atom that doesn't have any electrons. So a typical example is putting a proton, H+, onto a lone pair. The hydrogen didn't have any electrons, it's just accepting a pair from a lone pair. So if you look at H3O+, the oxygen atom has 3 bonds and 1 lone pair. If you calculate the formal charge, that's 6 valence electrons minus 3 bonds minus 2 unused electrons plus 1. And it doesn't make any difference how many ways you give oxygen 3 bonds. It can be a double bond and a single bond. It can be a triple bond. It's all going to come out the same. Oxygen is going to have a plus charge. So now what about nitrogen? Nitrogen typically has 3 bonds, so if you give it a 4th bond, have it donate its lone pair to somebody, then it's going to have a plus charge just like oxygen when it has an extra bond. So in the case of the ammonium ion, which is tetrahedral, 109.5 degree bond angle, nitrogen has 4 bonds, so that means that its formal charge is going to be +1. 5 valence electrons minus 4 bonds equals +1. Just like with oxygen, if you have 4 bonds to nitrogen, doesn't matter how you do it. In the case of the ammonium ion, double bond, 2 single bonds gives nitrogen a +1 charge. In the case of the protonated hydrogen cyanide molecule, a triple bond to nitrogen, a single bond to a hydrogen, gives that nitrogen a +1 charge. The only charged unhappy atom you'll have to worry about in organic chemistry is the carbocation. That's a carbon with only 3 bonds, no lone pair, so that carbon only has 6 electrons around it. It's very unhappy. It's trigonal planar. Formal charge, 4 valence electrons minus 3 bonds, no lone pairs, so +1. How do you get this? Well, in the example, if you have a carbon with 3 CH3 groups and a bromine attached to it, in water, there's an attraction between the partially negative bromine and the partial positive charge in the water. As that dipole-dipole interaction gets stronger, you get a weakening of the carbon-bromine bond. Eventually, you get bromide, which forms a true hydrogen bond to the water molecules. And you also get the development of more positive charge on the carbon atom that used to be attached to bromine. That is stabilized by interaction with the oxygen of water through a dipole-ion interaction. Now, this is not something which is easy to do. Carbon has to have the correct circumstances, such as having this attractive force to something like a bromine atom and hydrogen bond development. But it can occur, and therefore you have to understand how to deal with carbocations and that they exist. Practice problem 1. Determine the formal charge on each atom. All the lone pairs are shown. Also, fix the bond angles if necessary. Some of these structures are not drawn properly, so you really have to fix the way the bond angles are. Answers to practice problem 1. You can see in part A, I had to fix the bond angles between the H and C, double bond to N, and HCH. Those are all 120 degree approximately bond angles. There's a plus charge on the central nitrogen because you have 4 bonds and no lone pairs, so nitrogen is 5 valence electrons minus 4 bonds, that's a +1 charge. The nitrogen on the end of the molecule has 2 lone pairs and 2 bonds, so we have 5 minus 2, which is 3, minus 4, which is -1. And part B, you now have to straighten out that portion that was bent because you have a central carbon atom attached to 2 other atoms, so that should be 180 degrees, should be linear. There are no formal charges. In part C, the carbon with only 3 bonds and no lone pairs has a plus charge. The bond angles are fixed so that now you have about 120 degree bond angles where you should find them in the trigonal planar carbon. And in part D, there's a negative charge on the oxygen with 3 lone pairs. There weren't any issues with the shape of the molecule. Oxygen has a formal charge of -1 because it has 6 valence electrons, -1 bond, -6 unused electrons for a net charge of -1. Hybridization is the mixing of s and p atomic orbitals to make new hybrid orbitals. In the case of carbon, you have the electron configuration helium in brackets, which is 1s2, 2s1, 2p3. Now you can mix those s and p orbitals together to form 4 sp3 orbitals. Each of these mixed orbitals or hybrid orbitals is 1/4 s character and 3/4 p character. Hybrid orbitals will overlap head-to-head with other atomic orbitals to make the strongest possible covalent bonds. These head-to-head overlapping orbitals are called sigma bonds. These are the strongest covalent bonds, and hybrid orbitals only make sigma bonds. They don't make any other kind of bond, only these head-to-head type. So if you look at the examples, you have 2 sp3 hybrid orbitals overlapping to make a sigma bond, and on the right you have an sp3 hybrid orbital overlapping with a pure s orbital from, say, a hydrogen atom, making a sigma bond. Okay, so you can only make 1 sigma bond between 2 atoms. The reason for that is if you try to make more than 1 sigma bond between 2 atoms, you're trying to put more than 2 electrons in the same space between 2 atoms. That's a violation of what's known as Pauli's exclusion principle. So if you have 2 electrons in a region of space, you can't have any more there. How do you get more bonds between 2 atoms? As in the case of double and triple bonds, well, you have to do something new, something other than the sigma bond. So double and triple bonds only have one sigma bond. The other bonds are different. These other bonds in the double and triple bonds are the weaker pi bonds. They're made from side-to-side overlap of pure p orbitals. You can see an example of a pi bond on the far right. Now, when you're trying to figure out how many hybrid orbitals you have, figure out the hybridization, the number of sigma bonds and lone pairs on an atom equal the number of hybrid orbitals that that atom had to make. So let's see some examples. To start with, except for hydrogen, which is a pure s orbital, each nonmetal or metalloid starts with one s orbital and 3 p orbitals that it can mix. So that's your standard starting set. If you look at the example on the left, you have a nitrogen atom which has 2 sigma bonds and a lone pair. The pi bond that it has between N and C doesn't matter for hybridization, because that's made of pure p orbitals. All we care about are the sigma bonds and the lone pair. Those are made of mixing the orbitals, hybrid orbitals. So 2 sigma bonds and 1 lone pair is a total of 3 hybrid orbitals. So you have to mix an s orbital and 2 p orbitals. That gives you a hybridization of sp2. That leaves you with 1 p orbital left for the pi bond. Now in the central carbon you have 2 sigma bonds. Again, we don't care about the pi bonds. And that means we need 2 hybrid orbitals. That means that we have to mix an s orbital and a p orbital. So the hybridization of carbon is sp. Each of those orbitals is 50% s and 50% p character. The oxygen on the end has 1 sigma bond, 2 lone pairs. That gives it 3 hybrid orbitals, so we have to mix an s orbital and 2 p orbitals, sp2, just like with the nitrogen at the beginning. 1/3 s character, 2/3 p character for each hybrid orbital. If you consider the pi bonds now, which are not, again, hybrids, they're made from the overlap of pure p orbitals, the central carbon has a pi bond to the nitrogen and a different pi bond to the oxygen. Just like the way that sigma bonds can't occupy the same space, pi bonds can't either. So you can't have both side-to-side overlaps of p orbitals occupy the same space, and p orbitals fall along the x, y, and z axes anyway. So you'll have one pi bond which is along one direction and another pi bond which is perpendicular to it. And that's how they'll look if they're coming off the same atom. If you look at the example below, we have a molecule with various red atoms, and you want to figure out the hybridization of each of those atoms. So you may want to pause now before you see the results. What you're going to get is that nitrogen has 3 sigma bonds in a lone pair. That gives it a total of 4 hybrid orbitals, which makes it sp3. The carbon that has 4 sigma bonds is sp3 as well. The carbon with the triple bond and the single bond only has 2 sigma bonds, which makes it sp. And the nitrogen, which has a sigma bond and a lone pair, which means it needs to mix 2 orbitals, is also sp. This problem 2. Identify the hybridization of each red atom. Charges are given. Include lone pairs where appropriate to fulfill the octet rule. Answers to practice problem 2. In part A, the nitrogen has 2 sigma bonds and 2 lone pairs, which means it has 4 hybrid orbitals. That means it's mixing the s orbital and all 3 p orbitals, so the hybridization of the nitrogen is sp3. In part B, the carbon only has 3 sigma bonds, no lone pairs, so that makes it sp2. It needs to mix an s orbital and 2 p orbitals to form 3 hybrid orbitals. In part C, we have a nitrogen with 4 sigma bonds, So that's sp3 because we have to mix an s orbital and 3 p orbitals to form all 4 hybrid orbitals that make 4 sigma bonds. With the oxygen, we have 2 sigma bonds and 2 lone pairs. Again, that's a total of 4, so that makes oxygen sp3. With part D, we have a silicon atom, so here's a new atom. 4 sigma bonds, just like carbon, therefore the same, it's sp3, mixing an s orbital and 3 p orbitals. In part E, we have the oxygen with a negative charge, has 1 sigma bond and 3 lone pairs. You got to mix them all together to form 4 hybrid orbitals, which makes the oxygen sp3. Nitrogen has a triple bond and a single bond. You only count 1 sigma bond for each of those types of attachments. So nitrogen to oxygen, 1 sigma bond. Nitrogen to carbon, the other sigma bond. So we have a total of 2 sigma bonds. That means we have to mix 2 orbitals, an s orbital and a p orbital. So the hybridization of the N is sp. The same goes for the carbon, which has a triple bond and a single bond. You only have 2 sigma bonds, because you can only have 1 sigma bond between C and N, and 1 sigma bond between C and C. So that carbon is sp hybridized. In part F, we have the carbon with 3 sigma bonds that is sp2 hybridized. You have to mix 3 orbitals and s and 2 p orbitals. In the situation with a carbon with 2 double bonds, you have 2 sigma bonds, and that means you have to mix 2 orbitals, an s orbital and a p orbital, so that makes it sp. If you look at the carbon that is attached to that carbon, even though you have a wedge and a dash, don't worry about that, that's the geometry, it has to be tilted in this case, has 3 sigma bonds. You ignore the pi bond, right? So that means that it's sp2 hybridized. You have to mix the s orbital and 2 p orbitals to get all those sigma bonds. The carbon with 4 sigma bonds attached to that is, as we've seen before, sp3 hybridized. And then the oxygen at the end has 2 lone pairs, 2 sigma bonds. So again, it's a total of 4 hybrid orbitals, which is sp3. Now let's look at an application of hybridization. Stronger sigma bonds are created by hybrid orbitals that have more s character. So if you look at the example shown, and you want to decide which carbon-chlorine bond is going to break to form sodium chloride, when sodium thiolate, which is Na plus SH minus, reacts with the organic compound, you want to find the carbon that is least S character. So that means if you have to choose among sp3, sp2, and sp, sp3 is the carbon you want to pick, because that's only 25% S character. sp2 is 33% S character, and sp is 50% S character. So the weakest sigma bond comes from the carbon that is sp3 hybridized. And you only want to look at the ones attached to the chlorine because that's the bond that's getting broken. So in the answer, you see that the carbon-chlorine bond in the upper right corner, is sp3 hybridized. That's the bond that gets broken. That chloride is replaced by thiolate, and you get a carbon-sulfur bond. So it all makes sense just in terms of the strength of the sigma bond as it relates to the hybridization of the atom that's in that bond. More S character, stronger bond. Less S character, weaker bond. And faster reaction. This is problem 3. Predict the organic product of each of the following reactions and explain using hybridization. So what you want to do is look at how the reaction occurred, think about what bond broke, and then decide which bond broke based on the relative strength of the bonds, which is affected by hybridization. Answers to practice problem 3. In part A, the weaker carbon-bromine bond that breaks is the one in which the carbon is sp3 hybridized, has 4 sigma bonds, versus the other carbon attached to bromine, which is sp2 hybridized with 3 sigma bonds. sp3 hybridization means you have 1/4 S character, or 25%, versus sp2, which is 1/3 S character or 33%. And the hybridization with this lower S character, in this case sp3, gives you the weaker sigma bond. It's easier to break, so that's why SH-, the thiolate anion, attacks that carbon and displaces the bromide there. In part B, it's a comparison of the sp3 carbon attached to iodine versus an sp carbon attached to iodine. With sp3, it's 25% S character. With sp, it's 50% S character. So clearly, the carbon with less S character is sp3, thus that carbon iodide bond will break more easily. Thiolate anion, SH-, will displace the iodide at that point, and that's why the product is the one shown.